Hi, my name is Koen Vogel, and welcome to the second part of my presentation on the causes of climate change. I hope you've watched part one already, the presentation that demonstrates that climate change is not predominantly due to anthropogenic causes, so not predominantly due to atmospheric CO2 increases. If not, you may want to check it out first, because for what I am about to present you now, I'd like you to be convinced that the IPCC climate models are missing an important natural forcing. Why do I need you to be convinced? Well, let's face it, if the hundreds of IPCC scientists that contributed to the report have missed something, then that something was not obvious. So when I discuss the true reason the Earth's climate is changing, I need you to suspend any disbelief you might have for 10 to 15 minutes it's going to take me to present the hard evidence. The first video showed the fingerprints that this mystery process has left behind, so the observations of the geographical and temporal trends. It's worth remembering that these fingerprints are completely incompatible with global warming due to greenhouse gases, for example, the heating of the Arctic Ocean during the winter. This mystery process explains all these fingerprints, these observations. So by the end of the presentation, you'll see how all the data neatly fits into place like pieces of a puzzle. So if it's not CO2, then, well, what is it? It seems obvious that whatever it is, it must be hugely energetic to be able to heat the oceans by tens of zettajoule. For comparison purposes, the total annual human energy consumption is only half a zettajoule, so it has to be something really big. Yet the process is fairly slow but steady, as it only caused roughly 1 degree Celsius of heating over 70 years. I showed this schematic in the previous presentation. It shows the main energies reaching and leaving Earth. You immediately arrive at the conclusion that any energy heating the Earth must be directly or indirectly coming from the sun. The main areas of ocean heating, the Arctic and the Northern Atlantic, are very proximal to the North Magnetic Pole, so some kind of magnetic link seems promising but not obvious. Looking at the schematic and realizing that the IPCC are probably right in concluding that the variations in solar radiation are not causing climate change, you're left with solar wind as the only viable solar energy source. Many of you may be unfamiliar with this energy, as in our day-to-day lives it really doesn't noticeably impact us. But it does impact the Earth's magnetic field, and I'll demonstrate how it affects our energy budget. The solar wind consists of a stream of ions and electrons that are emitted from the sun's corona, or the upper atmosphere of the sun. These particles drag magnetic energy from the sun with them. The interplanetary magnetic field is embedded in these particles. This is still a poorly understood process. Just last year, NASA discovered that in the vicinity of the Earth, this interplanetary magnetic field was about 100 times larger than previously thought. For the purposes of this presentation, it's enough to know that the solar wind is highly energetic and consists of particles and magnetic energy. At the Earth's surface, we don't really notice the energetic nature of the solar wind, as its particles and energy are largely deflected by the Earth's magnetosphere, which is fortunate for us because I've read somewhere that if left undeflected, the solar wind would strip away our atmosphere and leave Earth uninhabitable. I don't know if that's true or not, but I hope and trust we'll never find out. But the Earth's magnetosphere is not acting like a shield whereby the particles and energy just bounce off like bullets off of Superman's chest. Think about what happens when you push two same-pole magnets together. The magnets change each other's fields, which in effect prevents you from pushing them all the way together. If you think of their magnetic fields as lines of equal strength, then the lines that come out of the magnet will change. They'll be deformed. That's what's happening when the solar wind hits the magnetosphere. It interacts with it and temporarily changes the Earth's magnetic field. Here's a graph from the Natural Resources Canada page that describes the measurable diurnal variation of the North Magnetic Pole position. So daily, the North Magnetic Pole position describes an ellipse with a maximum diameter of 85 kilometers. So they, as I, ascribe these variations to solar wind interacting with the Earth's magnetosphere. They claim these interactions cause electric currents to flow in the ionosphere and the magnetosphere. So how are these electrical currents created? What they're talking about are induction effects, similar to those of an induction cooker. Electrical induction occurs when a volume of magnetically susceptible material moves through a varying magnetic field. The induced electromotive force, E, is given by the Lenz-Faraday law equation. This is high school physics, and if this is unknown or mysterious to you, then I suggest you watch a YouTube video that demonstrates this. A classic video pushes a magnet through a coiled copper wire, induces electricity, gets a light bulb to burn. An induction cooker works using the same principle. An alternating electrical current through a coil causes a variable magnetic field that induces an electrical current in the pot you've put on the cooker. This induced current in the pot is converted to heat according to Joule's law, which you see here. Note that there's a factor of magnetic susceptibility missing from the equations. Ferromagnetic pots have a higher magnetic susceptibility than, for example, diamagnetic copper or aluminum pots. You can still induce a current in a diamagnetic aluminum pot, and it will still heat, but the energy transfer is less efficient. So magnetic susceptibility does not occur in the equations, but it does limit the amount of energy transfer that can happen. If you don't believe a diamagnetic material such as aluminum suffers induction currents, then leave a piece of aluminum foil on your induction cooker. Turn the cooker on, watch the foil melt, and destroy your cooker. So induction effects occur in all materials, but materials that have lower magnetic susceptibility will see lower energy transfers. It's just less efficient. Note that the negative sign symbolizes a direction. The induction current counterbalances the varying magnetic field. The sign is irrelevant for induction heating, as both increases and decreases in magnetic field strength produce an electromotive force and a heating effect. Copper is a diamagnetic material, so it's repelled by both north and south magnetic poles. And even though it's not ferromagnetic, induction effects can happen in copper. For example, copper wiring is affected by solar flares. Solar flares are similar to solar wind. They're violent solar coronal ejections that cause relatively large changes in the Earth's magnetic field. Changes that are so large that they cause induction effects in pipelines and electrical grids. For example, in 1989, a severe solar storm tripped the Hydro-Quebec power grid, which caused a severe power outage, so induced a severe electrical current on the Earth's surface. And this in a material, copper, that on the face of it is not ferromagnetic, so not that magnetically susceptible. Now, why am I telling you all this? This schematic shows what's happening. The solar wind and solar flares deform the Earth's magnetic field. These changes are also felt by the Earth's core, which is ferromagnetic. These storms cause the geomagnetic field to deform, whereby the Earth's core experiences a variable geomagnetic field. So the Lenz-Faraday and Joule laws predict that these storms therefore induce highly energetic electrical currents in the Earth's core, whereby the induced electromotive power is converted to core heat. That such heating is happening is not in question, otherwise we're invalidating the Lenz-Faraday law, which has stood for almost 200 years. Is there any physical evidence that such is happening? Well, yes. It's well known that the mid to late 17th century period of low solar activity, known as the Maunder minimum, coincides with the late 17th century geomagnetic field actual dipole strength maximum. To make the link, I need the help of these authors, Aubert and Finlay. They state that the Earth's magnetic field is produced by the Earth's ferromagnetic core via energy released during its cooling, so heat energy is converted to magnetic energy. Strong field variations are produced by rapidly cooling cores. Sunspots are magnetic disturbances on the sun's surface, so most of the solar flares and coronal mass ejections originate in the magnetically active regions around visible sunspot groupings. So periods of low sunspot activity coincide with low solar activity, low solar wind, and solar flares. During these periods, the solar wind is not actively heating the Earth's core through induction heating. So the core can cool and convert heat energy into magnetic energy. So its magnetic energy will increase, which is precisely what we observe at the Maunder minimum. So the Earth is behaving like a giant battery being charged by the sun. Now on this graph, you can see that the Earth's actual dipole strength has been decreasing since the Maunder minimum. Where's this energy going? It's not lost to space. It can't. There's no way the energy can be transferred. It's not lost to the solar interactions because they just increase the Earth's energy. It's very likely being lost to induction heating of the material outside the Earth's core, the Earth's mantle or its crust. The Earth is behaving like a gigantic induction cooker. Now, I mentioned before that the amount of energy transfer that can occur is limited by the magnetic susceptibility of the materials, so we're looking for preferably ferromagnetic material we can heat on our induction cooker. Pure iron and nickel are very susceptible. That's why we think they make up the bulk of the Earth's core. But large volumes of ferromagnetic materials are absent from the Earth's crust and mantle. Otherwise, we're left scratching our heads. Most sedimentary and igneous rocks are not ferromagnetic. Basalts, which form the bulk of the ocean floor, contain magnetic minerals, so probably are reasonably susceptible. But there's another, less obvious candidate, seawater. Salt water is diamagnetic in nature. If you don't believe me, just look for videos of scientists using powerful magnets to push grapes around. For some reason, they like to use fruit. Or there are other numerous scientific articles you can find with a quick Google search. If induction heating of seawater sounds like nonsense, then remember that copper is weakly diamagnetic too, but that changes in the Earth's magnetic field due to solar flares induce a current powerful enough to trip the Quebec electrical grid. So is there any additional physical evidence that solar wind is heating the Earth's core. We've already seen that the Earth's magnetic dipole maximum coincided with the Maunder minimum. Let's revisit Aubert and Finley. They tell us that the Earth's core generates two types of geomagnetic variability. The first is due to slow convection movement and results in centennial scale variations, such as that at the Maunder minimum. The second variability is caused by hydromagnetic waves and results in annual scale variations. Now, surface observable variability of the second type includes magnetic pole movements, for example, wandering of the north magnetic pole, and a phenomenon called a geomagnetic jerk. The term jerk is borrowed from the field of electrodynamism and refers to a relatively quick change in the second derivative of the Earth's magnetic field with respect to time. Geomagnetic jerks on average occur every 10 years, a number that is similar to the 10 to 11-year solar cycles, which suggests that there's a link between the two. Strong geomagnetic jerks were observed globally in 1901, 1913, 1925, 1969, 1978, 1991, and 1999. Let's see if we can relate that to induction heating of the Earth's core. A large change in the second derivative could be caused by a large change in the induced electromotive force, according to this equation. Now, this can occur when a decreasing solar wind trend switches to an increasing trend, so when the electromotive force changes sign. The heating and cooling episodes that drive their decadal to centennial geomagnetic field variability must be caused by a variable energy source that causes the Earth's core heat to fluctuate on decadal and centennial timescales. Magnetically induced heating of the Earth's core due to solar wind variations and solar flares is a very likely candidate. To test this, we can look at the solar wind variations. These have been measured since 1868 by the ISGI, the International Service of Geomagnetic Indices, as the AA index. I'll use the 1989 solar flare that caused the Quebec power outage as an example. As I mentioned before, it is a change in magnetic flux that creates an electromotive force. The ISGI data provide 3 hourly measurements of the AA index, so for analysis purposes, the delta AA variable was calculated as the difference between the absolute value of an AA index at a given time with the value measured 3 hours earlier. This AA index change is proportional to the magnetic flux change over the 3-hour time interval, so it's proportional to the induced electromotive force, according to Lenz-Faraday law. The squared difference is proportional to the induced Joule heating power, so a variable delta QAA was calculated as the yearly sum of the squared 3-hour differences. Delta QAA represents a measure of the yearly induced power due to solar wind variations, so variations in delta QAA are proportional to the overall induced energy heating of the Earth's core. Low delta QAA values represent periods of low induction heating, during which the core can cool by converting heat to geomagnetic energy, while increasing delta QAA values represent induction heating of the core and increasing core temperatures. The resultant data set shows an 11-year delta QAA cyclicity, which unsurprisingly is very similar to the 10 to 11-year solar irradiation cyclicity. Solar wind activity and geomagnetic storms are more prevalent during periods of high solar activity. Note that the large delta QAA peaks correspond to large solar irradiation peaks. Also note that the globally observed geomagnetic jerks largely correspond to years where the electromotive force switched signs. All this suggests that the geomagnetic jerk cycle likely consists of, first, induction heating of the core during increasing delta QAA, next, cooling of the core when delta QAA drops below a threshold value, conversion of core heat energy to magnetic energy during cooling periods, resulting in increasing geomagnetic field strength during periods of low heating, so during periods of low solar wind activity. Finally, a geomagnetic jerk when delta QAA is at a minimum, when the electromotive force switches sign. Okay, so there are good indications that the centennial scale solar cycles and the decadal scale solar cycles influence the Earth's geomagnetic field variability through induction heating of the Earth's core. Is there any evidence that these geomagnetic variability changes are responsible for any climate change? These changes in the geomagnetic field strength and orientation will cause induction heating in magnetically susceptible materials on the Earth's surface, for example, diamagnetic seawater. Is there any evidence that this is happening? Well, if you look at a map of the horizontal component of the Earth's field strength, you can see it's quite variable. Most ocean currents that traverse the surface will undergo induction heating due to the changing horizontal field strength. For example, the Gulf Stream originates as the North Equatorial Stream off the coast of West Africa, about 30,000 nanotesla. It crosses the Atlantic to offshore Florida, the field strength is 25,000 nanotesla, then traverses the Atlantic again to offshore Western Europe, where the field strength is now about 20,000 nanotesla. According to the Lenz-Faraday and Joule laws, the seawater in this current, which is diamagnetic, will be continuously heated as the current traverses the Earth's surface. However, as the field is relatively stable in time, most of such induction heating should be deemed part of the steady state, so can account for any recent global mean surface temperature increases. Any recent changes attributable to geomagnetic induction heating need to be attributed to recent changes in the Earth's geomagnetic field. A map of the Earth's predicted annual rate of declination, so changes in the direction of the Earth's magnetic pole, shows some remarkable similarities with the depth-averaged global upper ocean temperature trends for 1971 to 2010. Three of the main North Atlantic currents, the North Atlantic, the East Greenland, and the Labrador currents, show significant heating trends and traverse areas where the annual rate of declination change is relatively large. For example, the Labrador current traverses an area quite near to the North Magnetic Pole, which has been moving towards Siberia across the Arctic Ocean. This is what's causing the yearly declination change. So the declination change of the Earth's magnetic field represents geomagnetic variability that, according to the Lenz-Faraday and Joule laws, induces additional heating of all seawater bodies. The additional heating component will be larger in ocean currents because there's more variability, as well as during years when the geomagnetic field is rapidly changing, for example in 2020, when the greater declination changes due to a significant North Magnetic Pole movement are occurring. Arctic currents that pass through areas proximal to the North Magnetic Pole, such as the Beaufort Gyre and the Transpolar Current, can therefore be expected to experience the greatest geomagnetic variability and induction heating. As mentioned before, the North Magnetic Pole also experiences a diurnal variation, or daily variation, whereby it roughly follows an ellipse with a maximum axis of 85 kilometers, causing significant additional geomagnetic variability in and around this elliptical area. In this ellipse, the magnetic declination does a complete 360-degree turn. The Arctic is indeed currently warming faster than other regions, and is doing so mainly during the winter months. So see the first part of my video, providing clear evidence that geomagnetic induction heating of the Arctic Ocean is very likely occurring. Note that this heating accelerated around 2000, roughly the year the North Magnetic Pole entered the Arctic Ocean. Geomagnetic induction heating is always a positive forcing, and its magnitude increases when geomagnetic variability is high. The oceans will heat more during periods when the declination varies more, for example due to the acceleration of the North Magnetic Pole between 2000 and 2020. Testing the hypothesis that such heating affects climate change requires analyzing the relationship between geomagnetic variability and climate data variability. Now, geomagnetic variability is very difficult to quantify, so I've selected the North Pole speed as a proxy measure for the independent variable. The higher the speed of the North Pole, the greater the change in declination, the greater the geomagnetic variability. According to the IPCC, the ocean's energy increases account for 93% of the Earth's total increase in energy, so its variability can be seen as the true climate change attribution challenge. To test the hypothesis, the global upper ocean heat content anomalies were selected as the dependent variable. The North Magnetic Pole locations since 1590 are available from NOAA, so I downloaded the locations and converted them to yearly North Pole speeds using the Haversine method. The NOAA data features 5 yearly step changes that are an artifact of the 5 yearly magnetic model updates. So for the analysis, I smoothed the data using LUS. The NOAA server also has the global upper ocean heat content anomaly data, so I downloaded that and averaged them per year. Note that the ocean heat data are only available for the 1955 to 2019 interval, but that this period coincides with the main focus of the IPCC attribution investigations. The fingerprints of the North Pole speed, its temporal trends, are encouragingly similar to the observed global mean surface temperature and global upper ocean heat content anomaly trends. My first video demonstrated that these trends cannot be explained by the current IPCC climate models, the 1900 to 1945 increase, the post-World War II decrease, the 1980 acceleration, the sharp increase around 2000. All of these are unexplained by the IPCC climate models. A crossplot between the two variables reveals that a strong correlation exists between the global upper ocean heat content and the North Pole speeds. All of the negative global upper ocean heat content anomalies occurred when the North Pole speed was less than 18 kilometers per year, and nearly all of the positive anomalies occurred when the North Pole speed was greater than that number. I've created a sigmoidal model that can be used to predict global upper ocean heat content anomalies for North Pole speeds between 0 and 54 kilometers per year. Note that I've rather unconventionally plotted this figure with the dependent variable on the horizontal axis in order to highlight the asymptotic plateau of the sigmoid and to model the equation. Also note that the equation is an empirical summary of the last 65 years, so caution should be used when extrapolating beyond the 1955 to 2020 interval or when using unsmoothed North Pole speed data. The model contains three distinct areas. A positive linear correlation between the two variables exists for the 1955 to 1968 and the 1974 to 2011 periods. A relatively flat relationship, this low tail here, for the 1968 to 1974 period, during which little correlation exists between the two variables. Global upper ocean heat content decreases despite a fairly constant North Pole speed of around 5 to 7 kilometers per year. Now, a likely explanation for this feature is that the preceding 1964 to 1967 period was exceptionally cold, so the upper ocean layer may have acted as a temporary negative heat sink for this period. Geomagnetic induction heating failed to compensate further heat energy loss to space, resulting in even lower global upper ocean heat content anomalies. The break-even speed appears to be at 18 kilometers per year, so prolonged periods of low speed will likely result in net ocean heat losses. Other explanations could be that the loss smoothing caused some loss of signal detail, or the effects of other forcings are causing some scatter. For the 2011 to 2019 data, that's this high tail up here, a slightly negative linear correlation between the two variables exists. Global upper ocean heat content increases despite a slightly decreasing North Pole speed. A likely explanation is that the heat is accumulating due to prolonged warming. The oceans are behaving as a positive heat sink, whereby high geomagnetic induction heating overcompensates the energy losses to space. Other possible explanations could include that loss regression data were used for the analysis, so the decrease of North Pole speed may be an artifact of the smoothing. Post-2000 data points show significant scatter, which is likely an artifact of the International Geomagnetic Reference Field models. Or it could be the effect of other forcings, for example due to radiative forcing due to greenhouse gases. Or the relationship has somehow entered a new phase since 2011, for example due to the shift of the area of intense declination that has now moved to the center of the Arctic Ocean. So is geomagnetic induction heating causing the recent global warming? Is it responsible for the global upper ocean heat content anomalies? Three elements are necessary for demonstrating a cause-effect relationship. The first is a temporal precedence of the cause to the effect. Now both variables change fairly simultaneously for the yearly average data, so that clause has been met. The second requirement is covariation of cause and effect. This is demonstrated by the strong covariation that I just showed you. The statistical analysis reveals that the null hypothesis, no relationship between the two variables, can be rejected with 99% probability. The relationship is statistically significant. This demonstrates that any attribution of ocean heat variability should take geomagnetic field variations into account. The last requirement for a cause-effect relationship is there can be no plausible alternatives. Well, are there any? Certainly the most obvious explanation is induction heating of the ocean's currents. Consider that the ocean's regional heat anomalies largely coincide spatially with the main Arctic and Northern Atlantic ocean currents that traverse the varying geomagnetic field. The heating varies as a function of north magnetic pole speed, which was taken as the proxy for the intensity of the geomagnetic field variations, indicating that these variations play a role in the heating of the oceans. The reverse relationship, that heating of the oceans is varying the geomagnetic field, is implausible. Ocean heat anomalies occur throughout the ocean column, unchanging from top to bottom. As the geomagnetic field does not vary significantly with ocean depth, its induction heating occurs throughout the ocean column. Other natural and anthropogenic forcings mainly interact with the uppermost ocean layer, so require an as yet unidentified process that redistributes the heat throughout the column. Note that the southern magnetic pole shows much smaller movements, so induction heating due to the declination variation caused by the magnetic south pole movement will be significantly less. Induction heating due to the south pole movement is mainly limited to the heating of the immediately neighboring currents, such as the Ross Gyre. I explained this in my companion video. The ocean's energy variations are therefore very likely caused by the induction heating of the main ocean currents as they traverse the varying geomagnetic field. Though the induction heating of diamagnetic seawater only produces a weak induction effect when compared to ferromagnetic materials, such small effects are multiplied by the magnitude of the variations, the huge volume of seawater in the currents, the increased variability due to the currents, The non-stop nature of the process and the fact that at a given location the Earth's magnetic field and other geomagnetic disturbances do not substantially change with water depth. The energy transfer occurs over the full water column. The process could also explain why Europe experienced a temperature low during the Maunder minimum, from 1645 to 715. The extremely low sunspot activity, a proxy for solar wind activity, during this period meant that the Earth's core was no longer being significantly heated through solar wind induction. This meant in turn lower induction heating variability of the core, which in turn lowered the geomagnetic field variability, which in turn lowered the induction heating of the ocean's currents. A look at the North Pole speed for the full NOAA 1590 to 2019 dataset reveals that 2 of the 3 estimated dates of the Little Ice Age temperature minima, 1650 and 1850, roughly correspond to the North Pole speed minima. That the North Pole speed was less than 18 kilometers per year for the full 1600 to 1770 period, and 1770 is the third minimum, indicating that a similar process to the one I just described may be fully or partially responsible for cooler oceans and temperatures since the late 16th century. It also demonstrates how exceptional the late 90s to present North Pole speed is and its associated geomagnetic variability. So in conclusion, the companion video demonstrates that the natural and anthropogenic forcings recognized by the IPCC cannot fully explain the observed climate data variability. CO2 is not causing climate change. Radiative forcing due to greenhouse gases cannot explain the fingerprints that are adequately explained by geomagnetic induction heating of the ocean's currents. The first unexplained fingerprint are the global mean surface temperature and global upper ocean heat content temporal trends. So the 1900 to 1945 increase, the post-World War II decrease, the acceleration of ocean heating around 1980, and the sharp increase in global mean surface temperature and global upper ocean heat content since 2000. The second unexplained fingerprint. During the last 2 multi-decadal periods of global warming, so 1909 to 1941 and 1980 to present, the Northern Hemisphere was heating more than the Southern Hemisphere, the Northern Atlantic was heating more than the Pacific and Southern Oceans, and the Arctic was heating more than any other regions, and mainly during its winter. The third unexplained fingerprint, regional global upper ocean heat content anomalies spatially coincide with major ocean currents. And finally, the last unexplained fingerprint, major ocean currents are being warmed in situ and throughout their entire column. Geomagnetic induction heating of the oceans is the only process that can explain all these unexplained fingerprints. So it's a natural forcing that should be included in all climate models. So let's bring it all together. How does the sun's magnetic energy influence the Earth's climate? During periods of higher solar activity, the sun's energy, the solar wind activity and solar flares, interact with the Earth's magnetosphere and cause the Earth's magnetic field to deform. This creates a magnetic flux change in the Earth's core, causing an electromotive force and Joule heating. The sun's magnetic energy is temporarily stored in the Earth's core, similar to a battery. During periods of lower solar activity, the Earth's core can cool, and heat energy is converted to magnetic energy. This magnetic energy can in turn be lost to the oceans through induction heating. This additional magnetic energy causes geomagnetic variability, which in turn causes induction heating of the ocean currents. Prolonged periods of high geomagnetic variability can cause prolonged heating of the oceans and cause global warming as the Earth's oceans control its temperature. Many thanks for your attention. My 2 videos present evidence that natural forcing and non-anthropogenic forcings are largely responsible for climate change. If you agree, then I would encourage you to mail your political representatives and encourage them to sponsor a full review of the IPCC Climate Attribution Report before funding more CO2 initiatives. Thanks for your attention.